The More Loving One by W.H. Auden. Looking up at the stars, I know quite well that for all they care, I can go to hell. But on earth, indifference is the least we have to dread from man or beast. How should we like it were stars to burn with a passion for us we could not return? If equal affection cannot be, let the more loving one be me. Admire as I think I am of stars that do not give a damn. I cannot, now I see them say, I missed one terribly all day. Were all stars to disappear or die, I should learn to look at an empty sky and feel its total dark sublime, though this might take me a little time. All right, this was a poem by W.H. Auden, A-U-D-E-N, called The More Loving One. I liked it.
I liked it too, and I like the delivery too.
Yeah, so. All right. Now, who is that voice in the background, you may wonder?
I'm just wondering what this is. What are we doing? Oh, hey, Shen.
I don't want your disembodied voice in the background, so I figured I'd bring you on.
So it's like, how's it hanging?
I mean, it's hanging in there. Had a pretty full weekend.
Yeah.
I don't know. I feel a excitement for doing the show after a little hiatus here.
Life gets in the way, it happens.
Definitely does. So as a reminder to everyone, what are you watching, right?
What are we watching?
I mean, if you haven't looked at what's on the scrolling ticker on the bottom, it's SG2 on space. What I would like to say, the only weekly space show, and let's get it back on track with that, with your host, Shen Ge, that's me, and Leonard Kramer, who used to be called, previously, like there was
I changed it.
You changed it. So you're just Leonard now, which is
I'm just Leonard. I'm just Leonard. Just me.
Watch the previous episodes if you want to see what his other names were. But we talk about space. This is what we're here for, right? Or all sorts of things related to space or science, sometimes touching on philosophy or psychology or other things. But the last time we talked about neutrinos was episode number 63. Back in the year 2020, April 13th to be exact. So It has been almost 5 years now since we touched specifically on the subject. Although neothorax, as Leonard, as you mentioned, we did briefly touch on that.
The physicist neothorac. Yeah.
Just as a note there. I forgot to say, lovely headband as always. And flamingo.
Thank you.
Our shirt, so it's a wonderful fit.
I don't usually wear. I mean, I wear the shirt, for the show. Basically, it's sort of.
Really? I thought that's.
Yeah, I don't
go out. You just like this.
I don't wear this to the office or anything like that. But I mean.
Yeah, I hear you.
I do wear the headband. I do wear a headband to the office.
You do wear a headband. That's for sure. Oh, before I continue, I will say, if you like this show after you watch it, I mean, definitely you can feel free to support it on patreon.com/SG2 on space. And thank you to Kyle Baker, Sam Walsh, and John Graves for your kindly monthly donations. I will keep the ticker on the bottom running. And with that, should we actually talk about neutrinos? I mean,
is that what you wanted to talk about? I'm pretty versatile. I mean,
this is episode 222 with the title of being Neutrinos' Mysterious Ghost Particles.
Maybe we should talk about those then.
I mean, I figured we'd talk about it. So, what are these ghost particles, so to speak?
Well, neutrinos are tiny, nearly massless subatomic particles that are among the most abundant particles in the universe. And despite that in abundance, they are incredibly difficult to detect because they only interact through a very esoteric or one of the weak forces in the standard model of particle physics. We used to think that they were massless, but in fact, in the past 25 years, it's been discovered that they do have mass. So they're incredibly difficult to detect because they interact only through the weak nuclear force and also gravity, and so that makes them essentially invisible to most forms of matter.
So, how do you detect them?
Well, there are reactions that occur between neutrons and neutrinos that give off a high energy electron that then can be detected. But it's so weakly interacting that they say things like that they could. It's such a weak interaction that it's said that in order to stop them, you would need a light year. In order to stop one, you would expect to have a light year thickness of lead in order to detect them. That sounds almost incredible, but that seems to be that seems to be true. So let's see, having to do with how they were discovered. Well, first of all, let me just do an overview of the standard model. So the standard model.
Yeah, I mean, I'm wondering, like, if we're gonna build this whole picture.
Yeah, that's right. That might be best. So the standard model, it classifies all of the elementary particles. So most people know about electrons and protons, neutrons, and so forth. Protons and neutrons are made up of subatomic particles known as quarks. So physicists have organized all of these particles into something like a little mini periodic table of the like most people are familiar. If you've taken chemistry, you certainly have seen, even in high school, you've seen the periodic table of the elements. In particle physics, there's something similar to that, or physicists have attempted to organize the subatomic particles into a similar kind of table. Actually, I have the table. Okay, let's do this. Let's do that. Let's do that sharing screen thing.
Let me see if I just pulled it up right here.
Yeah. Okay, there's one. So
yeah, go ahead. So you can go ahead.
Right. So this is so this is the standard model, right? And it's known to be incomplete partly because of the observations about neutrinos. Really, the standard model, it classifies all the known elementary particles into two main groups. One of them is called fermions, and that's the stuff that matter, usually what we think matter is made up of. And then bosons, and that's the particles that carry the force. And really, Richard Feynman and maybe some of his proteges and folks that lived about the time he was active came up with this idea. So fermions are matter particles, right? And they consist of two different kinds of things. They're called, so I'm going down a hierarchy. So we've got fermions and bosons. Fermions are the things that matter is made of, known matter.
Okay.
And bosons
is fermions.
Right. And so bosons, and it's and you just kind of have to memorize this, or you just keep reading about it and you start to get used to it. I know when I was getting introduced to this topic, it was like I would just go blind, basically. I would just fade out because it was so complicated.
Like why are they so I mean, I can see, like, vertically speaking, or horizontally, however you say it, column wise, I mean, on the left side is fermions, these are matter. On the right side are bosons, which talks about the interactions between these matter, right?
That's right. And so that first column there. Oh, go ahead. Yeah.
Okay, you're probably going to explain it further, so let me just.
I was going to say that first column there is what most of matter in the universe is made of, and the other ones the three columns are called generations. right? And so the second column and the third column are extremely exotic versions of the these elementary particles that are known to exist. So what I was going to say is that so everything on that left group there are the fermions, and the right group are the bosons. The bosons consist of things like photons, and also these uh, um, photons, and another particle called a gluon. And I'll talk about these if you still have patience. And then there's these two weak force carriers. What?
I said plenty of patience.
Yeah, the Z boson and the W boson, and then to make it more complicated, there's two W bosons, right? So
can you explain a little bit what are these different let's just say like rows? Like why are they split into like 4 rows?
I don't know really what the rows are called, except that what's been observed is that there's the first 2 rows are there's an up quark and a down quark, and then the third row is an electron, and then the bottom row is the electron neutrino. And so those are the basic elements of subatomic particles that make up all of matter. The rest of these are artificial. For the most part, their existence in the universe is through artificial particle accelerator and very, very high energy processes, like in stellar explosions and that sort of thing. So that's very interesting, because they don't, the other 2 generations don't really, I mean, they exist, but they aren't really materially realized in most of the universe, except here on Earth in artificial experiments, which I think is kind of interesting. I'm not saying that they don't exist at all, but they are believed to exist in things like processes associated with with neutron star formation and extremely high energy. They all have the first column are the normal matter particles that we know of, and they are the lightest in mass. And that as you increase across the row, the masses increase.
So the neutrinos, they are like is that top left number like the mass, like it's like point not point, like less than 0.00000012. That's what it says.
Yes, so the neutrinos have extremely small mass, and we have a little trouble even explaining that. So there's some mysteries that are associated with that.
And it has a charge of 0 and a spin of 1/2.
Spin of 1/2. All the fermions have an intrinsic spin of 1/2. All of the bosons have an intrinsic spin of 1.
Right.
And that's and so that's related to a kind of exotic physical principle associated with Pauli, Wolfgang Pauli.
Right. I mean, if we want to okay, so let's go more into what the neutrino aspects themselves. Like I see here, like you have electron neutrino, muon neutrino, and tau neutrino. What does that mean?
Okay, so those are other neutrino. There's 2 other neutrinos that are associated with the second and third generations, and they are related to interactions with the mu particle and the tau particles, and then sometimes they call that muon and tauon. So we'd have to get into the history of this, but essentially, actually, it's not a bad idea to talk about the history from the little bit that I know. In the 30s. So in the So when all of this stuff was forming, when all of the theory about this was forming, it was observed that neutrons, that neutrons in an atomic nucleus would convert into a proton and emit an electron, and that's called beta decay. And so what was observed was a spectrum of energies from the electron. In other words, the energy was not quantized the way they usually think of it. And so people were thinking at that time, around the year 1930, people were thinking, well, where's the missing energy? They were able to measure the radioactive products. I mean, the decay products, and they would see an electron come off, and they could carefully measure the energy. Conversion of carbon 14 into nitrogen 14 produces an electron. And so what was observed was that the energy of everything on the right side, well, they didn't know about the anti-neutrino. Those two are sort of equivalent. This is has to do with the two different kinds of beta decay. Maybe we should just talk about carbon 10. It's less complicated. But so this kind of decay occurs, and it was noticed that the energy of the products was missing, and they had so Pauli wrote a famous letter to one of the conferences, where it occurred to him that this could be explained if there was a missing unobservable particle, because the neutrino wasn't observed because it doesn't interact with anything. And he said, what if there is a particle that is produced that carries off the energy, but we can't observe it because it doesn't interact? It's electrically neutral.
Okay. So he's basically, this whole thing came about because we predicted these particular decays, and there was missing energy, and there's no particle that was known at that time to be able to have that, and it wasn't detected. And so it's like, what is going on? This particle must not be.
He wrote this famous letter. The letter's in German, okay, but I think I've cited it a number of times, and it has to do with, he starts out by saying, "I'm sorry I couldn't come to the conference," or it says, Dear radioactive ladies and gentlemen," because the conference was all about radioactivity, about this particular topic.
That's funny.
And so he said, I think it was a joke. Nerds behave this way.
I mean, nerd jokes. Oh, there you go. I mean, this was translated from the German, I'm sure. But
does he say? And it says, "Dear radioactive ladies and gentlemen."
Exactly.
And I think the letter goes on for a while. One of his colleagues read it, and they circulated it. They reproduced it and circulated it around. And then I think at the end of the letter, he says something like some trivial personal thing about, well, I'm sorry I couldn't come to the conference because I had to go to a party, or something like that. But this, and then in the letter he says, I don't think this particle will ever be detected.
Why such, like, you start out a letter saying there's something there, and then you just have such pessimism on actually ever finding it?
Yeah, because the equipment and the techniques, the laboratory techniques at the time, they didn't think that they had any hope of ever being able to see it. But actually, I think 25 years later, it was detected, and eventually, I think, a Nobel Prize. So Clyde and Cowan in 1956, they confirmed the neutrino's existence, and they did it with using a reactor, a nuclear reactor, where they just they made a detector that would detect this rare reaction, because we just showed a reaction where the neutrino is given off. Well, the reverse reaction also occurs, and so they were able to confirm it. There's a story that they tell about someone proposed, I think this same group, Cowan and Rhines, they also proposed shortly before that they develop a detector to position next to a nuclear explosion, because this is where neutrinos come from. They come from radioactive decay and radioactive things like that. And so they said we can put a detector right next to a nuclear explosion, and we should be able to detect a bunch of neutrons that way. So they thought, well, one of the things is they had to worry about vibrations and that sort of thing. So they had this idea, it's a really cool idea, where they would have a nuclear explosion that would be used for the research that the military was doing anyway, and they would have like a tower next to it, a few hundred feet away, and so or 1,000, some distance away, but right up against the bomb. So when the bomb goes off, it would spray a lot of neutrinos into the instrumentation, and then they would drop it. It would be in free fall, and then fall into a hole deep into the hole, and then they would have something to catch it, like some foam rubber or old tires or feathers or something like that at the bottom of the hole. So, and then there was all kinds of jokes about, well, yeah, we would put a graduate student in there to monitor it, and then you'd fall, but they never actually did that. They found out that they could just position their instrumentation near a normal nuclear reactor, but it would just take longer. So they observed for months instead of microseconds.
Right. So this is a Cowan ring experiment.
Yes. So they won the Nobel Prize as it was late in 1995. That's a typical kind of thing. And so,
wow, look at these guys.
So another neat thing about the history of this, which I kind of like to talk about the history. It's just interesting.
Of discovering of news discoveries is always interesting.
Yeah.
Or old discoveries.
So in the 1960s, most of the neutrinos. So at this moment, there's trillions, and I'm not exaggerating. It's not there's trillions of neutrinos that are penetrating your body, every cubic centimeter of your body.
Why do I not feel anything?
Every moment, every second, just trillions of them.
Every nanosecond, even.
And you don't feel anything because they don't interact with you. They are electrically neutral, right? So then the reactions that do occur are so rare that it's just extremely difficult to detect. So in the 1960s, there was a problem that was observed, or there was a problem that emerged about most of the neutrinos that we do observe at Earth come from the nuclear reaction occurring on the sun. So what emerged at that time, and I remember reading about this in not as I wouldn't say as a child, but as a late teenager, 20s, in my, when I started becoming intensely interested in physics, there was a solar neutrino problem, because it appeared in the 60s and 70s, it appeared that the flux of neutrinos that were observed was about a third or less of what was predicted based upon the known properties of the thermonuclear reactions occurring on the sun. So let me say that again. So the sun is producing. The sun is a thermonuclear reactor, and yes, it's emitting neutrinos. But we're only detecting about a third of what we think is there. And so this was a big problem. And I remember reading about it in Scientific American and the different literature that I had access to. I wouldn't say growing up, but as I was, going to college and so forth. And then and all of this had to do with the presumption that the neutrinos are a zero mass particle. So if you're a zero mass particle, you have no choice but to travel at the speed of light. And if you travel at the speed of light, then no time you experience. If you travel at the speed of light, you don't experience any time. Right, because of time dilation,
so if you travel the speed of light, what happens?
You don't experience any time.
There's no time at all. Okay.
Right. So what was observed was that there was something called neutrino oscillation, And that means that the neutrino was oscillating between the different flavors that it has available to it. Those which
three
is
that we talked about, right?
those three columns. So it's a little bit of an exception to the rule that those. And so this was confirmed that the oscillation was occurring, and that meant that they had a mass, and they were able to detect the differences between the masses of each of these. And so that was a big deal. So they got another new Nobel Prize came out of that. That was the part of Kajita and Donald.
Ray Davis and Masatoshi Koshiba. Well, I mean, that's what this says. This guy and this
for confirming
experimental work, which found the number of solar to be around a third of the number predicted. And then, oh, okay. I see.
Kajita and McDonald got for confirming the neutrino oscillations, that neutrinos actually have mass.
Oh, okay, I get it. So basically, the experimental work found the number of solar neutrinos to be around a third of the number. They got the Nobel Prize for that, these two people. And then neutrino oscillations to explain what was going on. Neutrinos turning from one flavoring to another. Takiki Kajita and McDonald got 15. Okay.
All right. So that's the background, right? That's the background for neutrinos. What are they, and what's sort of what they're all about. The one other thing that I need to point out is that there's this property called spin and chirality. Chirality is related to something. Yeah, chirality is like, you know how your left hand is different from your right hand, even though they seem to be like, they're mirror images of each other. So
yeah.
So there's a property that's related to the spin and the direction of motion that's similar to that, right? And so neutrinos have all of the observed neutrinos that we know of are left-handed chiral, right? So I don't think we need to go into like the details of what all that means, but it has to do with the spin of the neutrino being aligned or anti-parallel to its direction of motion. So all normal matter neutrinos have left-handed chirality, right? And they operate through, and the weak force operates only on left-handed chiral particles or right-handed antiparticles. Okay, so it's like oh god, so complicated, you know. It's like there's so many complications, and so you have to that it wasn't made up for us to understand. It's just very complicated. Okay, but that's where we are with that. Okay, so to me, it's very interesting that there's this asymmetry, right? So that the particles only
so out of the four fundamental forces, is the weak force the only one that has this chirality?
Yes, that's right. The weak force is the only one that operates through the left-handed mechanism.
Huh.
You know?
Do we know? Okay, sorry, go on.
No. Okay, I know what you were about to ask.
Okay.
No, it's very mysterious, and it's a really big problem, and it really means, if I could put a big underline under this model is incomplete. I think that's what it's showing.
The standard model of physics, of particle physics, which is supposedly our most fundamental understanding of all the fundamental particles and how they interact, is clearly incomplete because it cannot explain why the weak force is only acting on left-handed chirality particles.
And I want to say also, I think physics textbooks that talk about this, everybody who talks about this just confuses things more and more and more, because even that picture that you showed, it just showed one kind of double particle. There's actually two kinds. Then all of these particles have antiparticles, and so it doesn't show that. And so
each of these, so like electron neutrino, muon neutrino, tau neutrino. So for the audience's knowledge, they have left chirality and right chirality. In addition, they also have anti-neutrinos for each of these.
That's right. So and that's left out of the pictures. There's so many things. There's so many holes in it, right? I mean, yet they show this diagram, and the physicist, the physics teacher, will smugly say, you know, this is, you know, how the standard model and so forth, right?
They feel like we figured out everything. Really,
right.
We don't know anything.
Okay, so yeah, we don't know any. Well, we know some things, but we don't know very much. Really, I really feel like we don't know very much. So this was also known, like in the 30s, 40s, 50s. You know, that there were these kind of issues, and so then some of the advanced topics having associated with this are whether neutrinos are what they call Dirac particles or Majorana particles. Okay.
It's Majorana.
Oh, Majorana. We've talked about him before. You forgot. He was a physicist in the late 30s who came up with this idea that that particles can be their own antiparticle.
Oh,
right.
That's right. Yeah. Yeah.
And so that would allow for a separate kind of a beta decay that is that has not yet been observed, but people are looking out for this kind of what they call double beta decay. And then, as an aside, we can remember Majorana as that physicist that disappeared in 1937. Decided he didn't want to live. He didn't want to be in the physics world anymore, and he disappeared. He took a boat to Naples and left a note.
That's right. And
yeah.
Right. Majorana. Right.
Yeah.
Okay. All right. Continue.
So anyway, he was a genius, but so okay, so that'll close the side note there. And then there's this other thing. So neutrinos.
This gets so confusing. Like you just get.
And so the reason I say that this is incomplete, and it's you know, it's like the profundity of the problem is such that, you know, we have this thing called dark matter, right? So neutrinos do, if they have mass, then they will participate in gravity. So but gravity is so weak that we have a great deal of difficulty utilizing gravity to detect anything. And so the presence of dark matter it just is a big it's a big red circle around all of this, you know, that's saying that there's something wrong. So there's the possibility that if there was something called, so we mentioned it was left-handed, right? All neutrinos are left-handed. But if right-handed neutrinos exist, it's possible there is a process where there's a speculative process, and it's called the seesaw mechanism. So sometime you'll see something about the seesaw mechanism.
Mechanism. I have not heard of that.
And that gives that has some solutions, some superposition solutions for very, very heavy particles, and then a very, very light particle, the manifestation of the two. And so the thought is that we know that neutrinos have mass, or at least two of the neutrinos have mass. One of the neutrinos could be zero mass or very, very light mass. And that could be associated with a very heavy right-handed. What I'm saying is the seesaw mechanism is a mechanism where there's an oscillation between the chirality of the neutrino. So the neutrino will switch from right to left or left to right.
Has this been observed to happen?
This has not been observed to happen. Okay.
Theoretical.
But theoretically, if a neutrino had zero mass, then right-handed neutrinos could exist from the Big Bang, could have been created at the time of the Big Bang, and they have nothing to oscillate into. There's nothing for them to seesaw against. Or if that purportedly zero neutrino had extremely small mass, then the decay could be on cosmological timescales, maybe billions or hundreds of billions of years, in which case we wouldn't observe it. Right-handed, so what I'm trying to say is right-handed neutrinos, if they existed, they would not interact through the charge, through the electric charge, and they would not interact through the weak force.
So how would you know what would they interact with? Nothing.
They would affect with gravity. And if there was a large, if there was a massive number of them, they would be responsible. They could be responsible for dark matter. So they're a strong candidate. In my mind, they're a very strong candidate for the existence of dark matter. So anyway,
that must mean there's a huge amount of them.
Well, there are a huge amount. I mean, neutrinos are the most abundant. The left-handed neutrinos that we are able to observe are the most abundant by orders of magnitude of all the subatomic particles. And if there was a right-handed conjugate through the seesaw mechanism, then it would also be a very, very abundant one, and it will also be very massive. So that's
okay. I see. The right-handed version is a lot more massive than the left-handed version.
Yes, right. So
and they don't interact with anything except gravity. Okay, I got it. It's going to be like how is the right-handed neutrinos, if they do exist, how are they created?
Well, they would be created at the time of the Big Bang. They are primordial.
Neutrinos are continuously being created, right, inside stars.
Right? Everything having to do with radioactive decay, any kind of radioactive decay, even a neutron by itself will decay into a proton in about I think I read 10 minutes. It's actually quite long that a neutron can exist, and then it will decay into a proton, an electron. I mean, a neutron will decay into a proton, an electron, and this mysterious neutron that flies off, taking much of the energy. Actually, it's an anti-neutron in that case. Right. So, but anyway, that was what I wanted to say. That was what I say. So the neutron. So really, let's put an underline. Put a bow on it. Neutrinos remain one of the most intriguing and least understood particles in physics. Okay, I would say their tiny mass and that flavor changing behavior is a challenge to the standard model, and it points to new physics that people need to be working on. Including the possibility of these heavy right-handed neutrinos. Sometimes they can use the word sterile neutrino. We don't know if they're Majorana particles, and if they are, then that's a further indication that there could be a dark matter, the link to dark matter. And it could be a key to unraveling some of the deepest mysteries of the universe and solving a lot of these problems. And I wish people would stop. I wish the science community or physics community would stop churning out string theorists and start churning out smart people who can think about these things. So
I knew it. I was waiting for another bash of string theory. Bashing. String theory.
The more I study it, the more I think about it, the more I think string theory is pseudoscience in the Karl Popper sense.
Right. There's a Nature article on what you call it, the seesaw thing.
Yeah. The seesaw mechanism has not been confirmed. It's speculative. But I mean, it's
counterparts of lightweight active neutrinos, abundant particle streams. The heavier neutrinos first thought to have come existence after the Big Bang are sterile because they interact with other particles only via gravity.
Yeah.
So, very interesting. Is this all these theories? I mean, how would we this particular theory, for instance, how do we prove it if it doesn't barely interacts with anything?
Well, there's a number of things. I didn't really make a list of the things that could be, but one of the things that occurs to me that that double beta decay that would establish the Majorana nature.
It's
of
Italian.
neutrinos. Yeah, Majorana. Majorano. I don't know. Sounds like some kind of sauce. Okay.
I was thinking that when you said it. I mean, maybe just because it sounds Italian doesn't mean it's good.
So, well, his story is so compelling. I mean, it's just so much. There's so much drama in the history of that. Majorana. I forgot what his first name. I think it was Luigi Majorana, or
Luigi Majorana.
Is that his name?
I don't. Wait, is it? No, it's not. You made it up. Majorana. His name is Ettore. This guy. Here, this dude, this person. That's what you're saying, right? We talked about him briefly once about
Ettore.
Yeah, like he disappeared and nobody knows what happened to him. So
yeah, nobody was. A picture appeared in 1958 of an older guy that looked like this picture in Venezuela, but it's really hard to believe that you could hide out, and why? I don't know.
Right.
What was his motivation? But
in any case, back to what you were saying. So how, like dark matter, possible heavy neutrinos, how would you find it?
I don't know. One thing you could do probably would be to establish that one of the masses of the known neutrinos. See, we know that there's 3 neutrinos, in that standard model, 3 flavors of neutrinos, right? And they oscillate, right? Which is how they resolve the missing neutrino problem, the missing solar neutrino problem. All right, so they oscillate. But the oscillation, the theory that's associated with the oscillation has to do with the differences in masses between those 3. So neutrino 0, could be a certain mass, and neutrino 1 could be flavor 1 could be a different mass, and so they could all be non-zero masses, but we only observe the differences. So if it happens that physics, nature has established that one of those neutrinos has 0 mass, then it could be coupled to a right-handed neutrino through the seesaw mechanism, and it would not oscillate. And so there could be primordial. You heard me say primordial. That's what your favorite word, isn't it? Primordial.
That's one of my favorite words.
One of your favorite words. So there could be primordial, heavy, right-handed neutrinos that are sterile, and they don't oscillate into that 0 mass neutrino, into the regular neutrino. And so they could be. It's very compelling because we know that there's something there, dark matter.
Yes.
And we don't have any other way of observing it. So this is a theoretical mechanism. So that's all I wanted to point out. That was what I wanted to. You want to talk about anything else?
I mean, what other things can we possibly talk about around here?
Well, you have a number of favorite topics. I mean, so.
Well,
Weren't you telling me the other day that you were going to get a tattoo?
Wait, what?
I just made that up.
Actually, you know what? I mean,
oh, you think it's a good idea? Huh?
I've thought about getting a tattoo.
Most young people have, yes.
Did you not think about getting it? Do you have one? Oh, you don't
have any tattoo. I stabbed my finger with a pencil in 1977, and the mark is still there. But I accidentally stabbed myself.
I was like, I mean, you're trying to give yourself a permanent mark, huh? Okay.
No, I wasn't. It was an accident. But
let's see here. Should I show something from one of these alien sites that I like?
Absolutely. It's the highlight of my week.
I don't know if this is Is this looks absurd? Okay, well, I have not seen this video. Does it like I don't know if it's gonna be terrible or what. I'm gonna ignore that one. Let me choose one which says object near plane disappears. So let's see how well this works. This is on UFOcasebook.com, which naturally, you know, is completely believable, right? So all right. So
Well,
let's
I
see.
mean, you know, it looks like they caught one that's not using the blurry film cloaking device. Wow, that's pretty compelling.
Is this real or is this? There we go. See, look at that.
Yeah.
Like that's so real, right?
Uh-huh.
And I don't know what's happening there. Okay, then is that just a human talking?
They look like people.
Okay, so that thing, and then this. I mean, it's a very clear video. Like,
Yeah, that makes it suspicious, doesn't it? Usually you want it so
okay. Here, let me
the aliens weren't
go back.
the aliens were not using their blurry picture cloaking device.
I mean, see, this is a problem with like these UFO videos. Like the real believable ones, you would think are okay. And then I don't know what that thing was, and I don't even know if this is part of it. That just seems like some random clip. Okay, but this part, like, so I don't know what to think because, like, if it's something that is so clear, it makes me think that somebody just put it there. You know, like,
Yeah, we're not gonna believe it no matter what we see.
although.
Right?
I mean, like, and if it's blurry, then you're gonna say like, "Hey, they're using like the blurry, like you can't even tell what's going on." If it's not blurry, you're gonna say it was like made up, you know? So like, there's no winning here.
There's no winning, right?
I mean, it's very unfortunate in my view, at least. There was something else. There was like a here. Let me go back. There was like an alien thing. Apparently, that somebody like they just showed up at their doorstep. I don't know if I believe that one. You're probably gonna think that's a little more absurd.
It wouldn't happen in Texas.
Let me see. Where is it? I don't know if the actual video. The videos are always hit or miss. You know, I never know if there's anything.
Yeah.
Here, let me try. Actually, no, forget that one. Let me try this one. Metallic top-like UFO seen in Brazil and USA. Okay, so this one was in Brazil in July last year. So supposedly, so let's see how well this is. So okay, skipping that. Come on. Okay, all right. Let's see. Yeah. So look at that. See. This is what I'm talking about. This looks authentic because this guy is like obviously a camera that's just going around, right? And then
yeah,
like what the heck is that? You know, broad daylight in July last year. Okay, skipping the Warner Bros. I don't know why that's. See these people who okay, but like that like what is happening, right? I mean, how do you explain it?
You want me to explain it?
Yeah, what's going on there?
Well, I mean, we can do like a fault tree on it, you know, or a explanation tree. So one thing would be it's a fake picture that we can start with that.
This is another way in Miami, Florida. Like what is that?
It's an alien. Okay, and another one's it's an alien ship from.
I'm going back here to show here. Let me just pause it when you see what's up there. Yeah, what is this? Look at that. What else could that be but an alien spaceship, right?
Well, I mean, it could be a fake.
Well, what could possibly be floating there? Oh, are you saying the video is fake?
The video, yeah. I mean, we can. I mean, you can these days, especially. But even in the 1950s, somebody could fake that. I mean, I remember seeing pictures as a child of you know paperback books with about UFOs. I was all onto that, you know, and they had pictures of pictures about this quality that came from the 50s and 60s.
Okay, so could be a hoax.
People can do amazing things with photographic film, even if you don't, just in a dark room. In the when photography was new, people would use they would do multiple exposures, and so that's how they photographed ghosts.
That's another topic that I will talk to you at a different time.
Okay. I'm open to all kinds of stuff, talking about.
I have weird theories about ghosts too.
Okay.
Which are unrelated to UFOs and aliens.
I'm open to it. I'm not so open that my brains have fallen out, but I'm.
So, okay. Yeah, I mean, I don't know. This maybe I'm just gullible, but it seems convincing enough to me.
Maybe you're gullible, yeah.
Wow. Don't have to agree, but if I take some time and go through this website, I'm sure I can find something that could be like unexplainable, even if you're saying like it looks too good to be, fake. But you can't. There's like a happy medium ground, right? It can't just be like completely messed up, like blurry, because then you can't tell what's going on. But you can't be like near perfect, because then you're gonna say they just made up the video. So there's something.
No, I would say that if there was a phenomenon like this, if you had a lot of witnesses, and you took each of the witnesses aside someplace and interviewed them separately from each other. That, to me, that would be a kind of compelling kind of evidence. If they all started saying the same thing, right? Then I could believe that actually something happened, right? But a lot of people have been, claimed to have been abducted by aliens and taken up in this spacecraft, and the aliens have done things to them unspeakable.
No need to go into details here.
Right.
So, I mean, if you were abducted by aliens and had these things done to you or not, whatever, let's just say you're abducted, and then you try to explain to your fellow humans what happened, and you're only met with skepticism and being told that you're lying. I mean, how would that make you feel? Like,
if I was abducted by aliens, I probably wouldn't believe it myself.
You don't have to be abducted by aliens, Leonard. You may not.
I am an alien.
That's what you say. So, yeah. Well, I mean, I like, when people say these things, I like to give them the benefit of the doubt. Like if they're a perfectly mostly sane person, I'll be like, why are you making up this story? I mean, there's got to be something, like maybe some truth to it, or at least you believe it's the truth. So, yeah, that's the thing, right? Okay, disbelief from Leonard's face. I can see it. Okay.
Well, but not. I'm open to it, and we can talk about life. The origin of life sometime.
We did talk about once or twice. We did, and we had that episode where you essentially declared that life is very unlikely to have existed at all, and you're surprised that you even exist.
I think the formal probability, the Bayesian probability that life appears anywhere in the universe is
zero. That's what
almost zero. I didn't say it was zero, but I said it's almost zero. I think we should do a show on that. Can do a show. We can do a
probability of life.
The Bayesian priors, what they call Bayesian estimate of. Let's do a show on the Drake equation.
What's that?
We'll do a show on the Drake equation, because a lot of things have been converging. Since the Drake equation is the probabilities, cascading probabilities of all the things that have to happen, and for there to be a civilization, a communicating, intelligent civilization.
Indeed. Okay, we can talk about that next time. Also, the Bayesian statistics about how unlikely you think life exists.
Bayesian just means that you do. do some kind of scientific assessment of what the probability is based upon the nature of your situation, not on based on repeated observations. I don't know what the opposite of a Bayesian is, but Bayesian is like if I know my uncertainty based upon the principles associated with the state of my situation or the thing I'm trying to predict, then I can say something about what the probability of an event is. But the other way you can talk about statistics is I do a lot of observations, make a lot of measurements, and so I get positive results and negative results and make a distribution and that kind of thing. So, but that's what that means.
I'm gonna have to read up on that.
And I think that from everything, I think that life is irreducibly complex, and this doesn't have to do with any kind of religious impulse on my part at all.
Well,
right?
I mean, you yourself have admitted to not have that kind of religious compulsion, so to speak.
It is a critical assessment of the in the Popperian, in the Karl Popper sense of what is falsifiable, what do we observe, right? And so we can talk about it. Let's do a show on it next week.
And who is Arnold Munez? No idea, but something about the Westall UFO incident. I'm gonna have to do a bit more research on that.
I don't know.
I think this is what we're saying, or at least what Arnold's pointing out. Like, you want to talk like in terms of.
I know. People get very upset at me. Right. People get upset at me because I don't. And it's like it must be because there's something, but it's just
Yeah, I'm gonna get together like a whole list with supposed witnesses and then and news articles attached to it.
Okay, I'm not going to talk. I'll listen to all of those things.
All right. I mean,
I can probably produce interviews with people who are institutionalized and.
Oh my God! Okay. All right. Okay. So, Leonard Kramer, the ultimate skeptic here. So that's what I see. All right. Thank you, Arnold, for bringing that up.
Thanks, Arnold.
We will discuss the Westall UFO incident at some point in the future, where Leonard will remain unconvinced. That's what I was for.
I don't know. No, that's not true. Okay, don't say that. I mean, I can be convinced. Okay, but I have some observations that you need to answer. Okay, so see, right. Anyway, we're over time, almost over time.
We're pretty much always over time. I mean,
we're always over. When we target 30 minutes, and we always end up being an hour. So
okay, so let's just go for an hour and target that. All right, thank you, everybody. This has been SG2 on Space, the only weekly space show. Be sure to go on YouTube and follow this, share, do all that wonderful stuff. SG2 on Space. And feel free to support us on patreon.com/SG2 on Space. You actually could just follow it without donating anything, since I put up posts there at times as well. So feel free to do that. And with that, Leonard has something to say. What is this?
Yeah. So on YouTube, there's like a little bell. Okay, if you click that little bell, then you'll get a notification. I understand you'll get a notification, right? And also make comments. You guys are. Where do you guys come from? Something like that. Try to. Be respectful.
I mean, most people who watch this are respectful. I mean, we're
most of the time. Yeah,
most of the time. Yeah. So, with all that said, thanks again to our patrons, Kyle Baker, Sam Welsh, John Graves, and also I always put out Toon Ryan there. Why not? He helped support the show for 2 years, so
we love him. Yes,
exactly.
Lord Ra.
With all that said, we shall say good afternoon for now if you're watching this live.
Arrivederci. Arrivederci. Shalom. Namaste. Good afternoon, good night, and goodbye.
Yay.
Mwah.